In this video, we will take a look at a few algebraic properties of the matrix operations that we previously defined. And those operations are matrix addition, scalar multiplication, and matrix multiplication. So this video we will look at a few theorems. Each theorem will have multiple parts. I won't prove each part, but I'll pick at least one out of each, possibly each group to prove, just to give you a sense of, how do we go about writing down general mathematical statements where we try to establish certain properties, right? So one of the things that we will realize is if we make a claim about all matrices or all matrices of a particular type, we can't establish that claim by using a specific example. We can illustrate it using an example, but that does not explain why it works for all of the matrices or any type of object that we're referring to, right? So let's look at our first theorem. And this theorem, it deals with properties involving scalar multiplication as well as matrix addition, right? So let A, B, and C be M by N matrices, and C and D are real numbers or scalars, right? And that's all we need. And then, so here are the conclusions. So the first one is the familiar commutativity property, right? So it says that A plus B is the same as B plus A, right? So now the property that we're used to with real numbers and functions also holds for matrices. Second property has to do with, well, what if we're adding three or more matrices together? So, how do we do it? Does it matter how we group them? Well, it doesn't. And this is the associativity property of matrix addition. So let's say you have three matrices that you're adding. You can add the first pair and then the third, or you can add the last pair, right, and then the first, right? So the way you group your terms when you're adding, it doesn't matter if that operation is matrix addition. And again, this is a property that we've seen several times. The third one has to do with the associativity, associative property of scalar multiplication. So here are the two scalars that I just defined, C times D. So if I multiply the scalars first and then multiply the matrix, I'll get the same result as if I multiply by D first and then by C, right? So in other words, if you happen to have like 2 times 3 times a matrix, you can either do 6 times the matrix or 3 times the matrix and then 2 times that result, right? So if you have multiple scalars multiplying your matrix, then you can kind of do it in stages, or you can multiply the constant first. This property is saying that you'll end up with the same result with either order of operations. Fourth property, this one's again seemingly fairly obvious, but it's an important one. If we take a scalar of 1 times our matrix, it doesn't affect our matrix at all, right? Because think about how we do scalar multiplication for matrices. We distribute the scalar to all the entries in the matrix and then multiply. Well, if you're multiplying all those entries by 1, the entries won't change, hence the matrix doesn't change, right? So that's actually kind of a verbal, proof of that particular statement. 5 and 6 have to do with the distributive property. the first version says this, and this is probably the more familiar one. If you have your constant or scalar times the sum of a plus b, or the sum of a and b, we can distribute the c to both these matrices. So this is CA plus CB. And then finally, our sixth one, if we have C plus D, so if we're adding our scalars and then multiplying the matrix, we get the same result if we scale A by C and then A by D and then add the results together, right? Now, many of these are so familiar that you just kind of take them for granted. But again, whenever you start doing algebra with different types of objects, and when I say objects, again, like a matrix is not the same as a function and is not the same as a number. So we have to be careful in terms of what properties we think we can just arbitrarily apply. They might not apply, right? And that's why we rely on these theorems. So here's just a proof of I'll prove the first one, right? It actually is a little one-liner. And this is what I'll say. So when we're proving these properties, we cannot use like a specific matrix or a specific pair of matrices. It has to be general. And when you think about the general form of a matrix, we just have the letter notation like we have here. We have the square brackets and with the Aij, and then we have it when it's written out where you see the A11, A12, etc. I'm going to go for the middle one, and I'm going to say let A be equal to this array of entries, and do the same thing for B. But again, I can't use A, I have to use a different letter, so I'm going to use the lowercase b, I, j. I don't need to restate the fact that they're all m by n. I mean, you can, but again, this is a part of the hypothesis. Now, what I will say is that the entries in our matrix are numbers. For us, most of our matrices are going to be with real numbers. So since Aij and Bij are just real numbers, we know that Aij plus Bij is the same as Bij plus Aij, right? Because these are just numbers. These are real numbers. But we're going to use this property to establish the fact that matrices have the same property under addition, right? So let's write it down. So if we have A plus B, well, we defined how to do this operation previously. And the way we add two matrices is we form a third matrix by adding the corresponding entries of A and B. Again, so this step is simply by definition, right? That's what we did previously. And now apply this property to say, I know because the entries are now numbers, I know I can change the order of operation as far as addition is concerned. I can apply the commutative property of real numbers right here and write this as Bij plus Aij. And then, but this is how we would define the sum of matrix B plus matrix A. So in other words, this is B plus A, right? So both of these, so this step right here is by definition, this step right here is by definition, this step right here is by the commutativity of the addition of real numbers, right? And that's our proof. So that's our QED. And never once did we write down a specific matrix or specific numbers. We kept things entirely general, using properties that we know, using definitions that have been established. And that's basically what, proofs entail. Yes, there are some proofs where you have to do something clever, something a little out of the ordinary, but that becomes ordinary the more you do it. It's like the first time you do something fantastic. Well, if you do it every day, it's no longer that fantastic. It becomes routine. It's the same idea with proofs. It's just that many people don't have the interest to really invest a lot of time in proofs, right? Okay, so that's our first one. And again, a lot of these properties are extremely familiar and should become and just out of habit easy to use. Now, one of the things from real numbers that is very important is the concept of the number 0, right? Because without 0, we can't do a lot of things. And what we want to establish for matrices is a kind of matrix that has similar properties to the number 0, right? So, and we call it the 0 matrix. So the 0 matrix, and how is it denoted? Well, we usually, it's like a O, like a big 0, because again, we typically use the uppercase letters for your matrix. So I guess you can think of this as an uppercase O. And sometimes you might put the dimension at the bottom here, right? And so the 0 matrix, often denoted like this, all it is filled with zeros. So is filled with zeros. And this is not so foreign to us, because, for instance, in our work with linear systems, we saw many times where we ended up with at least a row or maybe multiple rows filled with zeros. Well, this is just saying that every row now is filled with zeros. And what does it look like? Well, for instance, here is the 2 by 2 0 matrix, right? 2 rows, 2 columns, all filled with zeros, right? And then you have obviously changing the dimension, you just have more entries, but they would all be filled with zeros. And one of the things that the 0 matrix allows us to do is the fact that if you were to take any matrix A, like one of our m by n matrices up here, and if I add it to the corresponding 0 matrix, again, that matrix shouldn't change, because I would have, for instance, Aij plus 0ij, because 0 is in every position. And again, because of what we know about real numbers, the sum of any number and 0 is always that number. So here are a few properties that all involve this 0 matrix, right? So I think just maybe in the spirit of time, I'll skip any of these. But basically, so all we need is one matrix now. One matrix, one scalar. And then we can say this. So if A is an m by n matrix, and C is our scalar, then, right, and this is a shorter list. In fact, it's half the length of the previous list. But our first result is this, and this is basically what I just verbalized. If you take your m by n matrix, and if you add the corresponding m by n 0 matrix, right, and and again, because of the commutative property of addition that we just proved, it's the same as doing this, right? So plus A, right? So no matter how we add it, what order of operation is, the end result is the same matrix A, right? Important property there. Number 2, and this one has to involve like the negative of a matrix. So if you have a matrix A and you add the negative of that matrix, and again, it doesn't matter the order, so I'm not going to write it twice, but again, we know we can switch the order around. Well, it turns out if you add a matrix to the negative of that matrix, all the entries are going to cancel out, meaning you'll get the zero matrix of that same dimension. So 0 m by n. And there is a word that we use to describe the relationship between a matrix and its negative. We refer to its negative as the additive inverse, right? So in fact, let me write that over here. So the additive inverse, so the additive inverse of A is negative A. And the zero matrix is called the additive identity, right? So 0 m by n is called the additive identity. Meaning, when you perform addition with this matrix, it doesn't change anything, right? So that's the additive identity. And then, like I said, there are 3, so here's the third now. The third is the one that involves our scalar, and it's basically this. It says, if a constant, or the constant, times my matrix somehow gives us the zero matrix, then one of these things would have to be true. Either the scalar is 0, so then either C is equal to 0 or A is equal to the zero matrix. And this property here, again, it's one version of the property that we use whenever we're factoring, and particularly with polynomials where you would factor. And if you have a 0 on the one side of the equation, then either of the factors would have to be 0. But in this case, one is a scalar and one is a matrix. So either we have the constant equals 0, or the matrix equals the zero matrix, right? So again, a lot of these are fairly obvious, fairly straightforward, right? And in the spirit of time, I'm going to get to the last group of properties that I want to mention, and this has to do with now matrix multiplication, right? So again, we're looking at all these standard operations and what are some of the properties. So this is our third and last theorem for this video. In this one, we need 3 matrices. So let A, B, and C be matrices. Now, since we're going to do matrix multiplication, we know that's a little bit more complicated. So what I'm going to say is that these are 3 matrices that are compatible under matrix multiplication, right? So we can say be matrices that are compatible under multiplication. Meaning if I write down the product AB, then I would assume that that's a product that can be computed, right? Otherwise, we could spend a little bit more time saying, oh, the dimension of this. We can write it down generally, but then we would have to make sure that those two numbers are equal, those two numbers that we have to check whenever we're doing matrix multiplication. Otherwise, it's easier to say that, yes, they're all compatible under matrix multiplication. Right? So we have this, and again, we need a scalar, right? Because again, we have all these operations, some of which involve scalars. So there are four of them on this list. The first one is the associativity property of matrix multiplication. So in other words, what if let's say I decide to multiply all three of these. So A times B times C. Well, how do we do it? Doesn't matter. Well, I could group the last pair, compute that product, and then multiply the product by A, or I could group the first pair, compute that product, and then multiply that product, or multiply C, and it turns out we will always get the same result. But it is very, very important to note that I am not changing the order that the letters appear. All I'm doing is I'm changing the grouping. So I might be changing the order of operations. In other words, doing this product before doing this product, but I'm not changing the order of the factors, right? In fact, let me just make a note, and we saw this in the previous video, that A times B is not necessarily equal to B times A, right? So again, just as this is not a property of matrix multiplication, right? Now, there are some special cases where, yes, the order doesn't matter. But in general, and we saw examples of this, where changing the order of matrix multiplication will completely change the answer, or sometimes one of these might be defined and the other one not defined, right? But if AB is equal to BA, we say that the matrices commute, right? So we say A and B commute, right? Again, so the reason I want to mention this is I want to show you that many times when you're working with real numbers, not only can you change the grouping, but you can change the order of the factors. Doesn't make a difference. It makes a huge difference in matrices, which is why in terms of the order that the letters are listed, it's still ABC, ABC, it's just how they're grouped, right? So what else can we do? Well, there is a distributive property as well for matrix multiplication that looks like this. If we have A times the quantity B plus C, we can distribute the A as long as we don't change the order. Again, notice it's in the letters appear in the order A, B, C. Well, if I distribute it, I will have AB, right? And then plus, again, distribute it, and then this would be AC. But I cannot change the order again, right? Can't change that order. So we have our distributive property, and it works similarly to the earlier pair of distributive properties that we stated. That one was with a scalar. Now this one is with a matrix. And the other version is this. If you have A plus B, that quantity times C, well, we can distribute it again. What has to happen is the C has to stay on the right. So this becomes AC plus BC, right? And then finally, here's where we need our scalar. If we have a scalar multiplication times a matrix multiplication like that, then it turns out what we can do is the scalar, we can change the order. In other words, we can put the scalar like in between them, or we could group them. So there's several ways we could write this. CA times B will yield the same result. And then A times CB will also yield the same result. And in fact, we could actually take the constant and put it all the way on this side. So here's another version of it as well. If you wanted to do AB and then times C, that would also be true. But notice, in each, so there are 4 possibilities here that are listed, but in each possibility, A, B is kept. That order is the same. AB, 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 right? We can't switch it and write it as BA because of this, you know, it's like this big thing in red. Say, do not do this. We can't do it in general, right? And there we go. So we have a lot of familiar properties, a lot of them. The only one that really sticks out as a big no-no is the commutativity property, or lack thereof, of matrix multiplication, right? But these are operations that we will do over and over and over again. So it's nice to see the properties, to say, okay, when you recognize these expressions, think of the variety of ways that they can be written, and you won't be breaking any laws, right? The only one, the one that's really saying let's not do this, is this particular property, right? And I will see you in the next video.